Good morning, everyone. Yeah, are you up for just one more astronomy talk? Yeah, let's do this. So this is obviously not to scale, it's an artist drawing of the solar system as you and I would have been taught in school. Anywhere from 1930, when Pluto was discovered, to 2006, when Pluto was booted out of its status as a planet. And we'll come to that. We'll talk about that whole business. But over the last 30 years, astronomy has come so far. Huge, massive telescopes. I can see the Keck telescope, the twin telescopes up there in Mauna Kea, rovers on Mars, Hubble Space Telescope and other space telescopes, probes out to the outer solar system to new horizons, and supercomputers that are crunching large amounts of data and able to create computer simulations for us about planetary motions and what have you. And that's really changed our view of the solar system. And that's why today's talk is titled, A Journey Through the Solar System, the Sun and Planets Through Modern Eyes. If there's 3 take-home messages that you take home from the entire cruise, the solar system really is all about the sun. The planets come in 2 distinct groups, which we're going to really focus on, and each planet appears differently for specific reasons. Okay, so let's just talk briefly about the sun. We talked a little bit about the other day, so I'll keep this bit brief, but this is an actual image of the sun taken by NASA's Solar Dynamics Orbiter. Essentially, the sun is a large ball of extremely hot gas known as plasma. It's self-illuminating, so it generates its own light and heat as opposed to reflecting light and heat like the planets do. And it's fueled. What fuels all that? Nuclear fusion at its core. The temperatures and the pressures, because of gravity, raises the temperatures up to 15 million degrees for the sun, and it's fusing small hydrogen into larger helium atoms, and in the process, huge amounts of energy gets released. Here's just a video clip I've got here of the sun's surface up close. So this is real general footage. And just near the end, they actually show you, they put an image of the Earth to scale. And what you'll see is just loops of hot plasma rising these magnetic fields, and it's going up, magnetic fields come up out of the surface of the sun, and that's all hot plasma, just extremely hot gas coming up. And you just look at that and you might think, oh yeah, okay. You wait until they show what the Earth looks like in comparison. There you go. There's Earth. Puts it in perspective, doesn't it? So it really is all about the sun. That's a to scale diagram there. You can see all the planets dotted down below. Over 99% of all the matter or mass in the solar system is all in the sun. As we spoke the other day, the planets just really are crumbs on the kitchen bench after you've baked your cake, which is the sun. Volume-wise, the Earth will fit into the sun 1.3 million times. So that's just briefly the sun. We're really going to focus on the planets. And the first thing you'll notice about the planets is they come in 2 distinct groups. So down here, you've got 4 inner, small, rocky planets, relatively sort of close together. And then you've got these 4 large outer planets that are mainly ice and gas and much spaced further apart, which you'll see. What I want to do is give you an idea of that to scale, but also talk about each planet individually with what we've known from modern technology and image and so on. But I want you not only to see what each planet looks like, how it appears, but I also want you to be able to understand why each planet is as it appears to be. And I think that's probably the most important thing. Not only to observe things, but to understand why things are as they are. Okay, so let's look at the scale distance of the planets from the sun. There's just a thing here. This represents the sun, this big yellow blob here. And I've drawn a line out, and these marks on the line is where we'll fit the planets in. Astronomers, when they measure distances in the solar system, they use what they call the astronomical unit. And an astronomical unit is the distance between the sun and Earth, which is 150 million kilometres. And that's considered one astronomical unit, or AU for short. And that's how they measure things in units for the solar system for distance. So, what's the first planet up, guys? Mercury, yeah. So let's put Mercury sitting in there. And that's at one astronomical unit. It's rather 1/3 of an astronomical unit. So it's 1/3 of the distance between the sun and the Earth. Pretty close. So that's Mercury there. That's an image taken from NASA's Messenger mission that flew past Mercury and then was in orbit from Mercury from 2011 to 2015. So in 2008, as it did a flyby, it took that image. It's about 1/3 of the size of Earth, and that's highly relevant to how it looks. So first impression, it looks like the moon, doesn't it? It just looks all pockmarked with just craters, impact craters everywhere. And you'd be forgiven to say, oh, that looks like a picture of the moon. Absolutely. So the question is why? Let's just take a step back and do what we call comparative planetology. Compare things back to Earth or another planet to make sense out of it all. Why doesn't Earth look like that? 2 or 3 big reasons. One is we have an atmosphere. We're big enough, also with enough mass on Earth to hang on to our atmosphere. We're reasonably distanced from the sun, where the sun doesn't strip it away, all the solar wind particles. So we've got an atmosphere. And the atmosphere does 2 things. It breaks up and fragments and sometimes even absorbs a lot of small to medium-sized meteorites and asteroids that are coming in. It breaks them up, and by the time they hit the ground, they're a lot smaller and they don't create big craters. The other thing is the atmosphere does, it provides to have air which can then support wind and rain, which is weathering. So when a crater does develop, you get erosion through weathering, through the wind and the rain and rivers and oceans and so on as well. The other reason that we don't see craters like this all over Earth is that we've still got a lot of heat. There's a lot of heat inside the Earth coming from the core. It's molten. And that heat rises up through the Earth, and that drives geological activity. That is volcanoes that erupt and spew everywhere, pushing out lava and what have you, and that covers rough surfaces. We have tectonic plates that are driven by that as well, tectonic plates moving around, sliding over the top of one another, renewing Earth's surfaces. So that is why Earth does not look like that. The reason Mercury is because it's relatively small, only 1/3 of the size, so it hasn't got the mass, the gravitational pull to hang on to an atmosphere. Furthermore, it's close to the sun, so a lot of the solar wind would strip away it would erode and strip away any atmosphere as well. So it can't really have an atmosphere to do it. And the other thing is, because of its small size, it's just a geometry thing. When you get a small sphere has a larger surface area to volume ratio. Given its volume, it has a larger surface area. What happens with surface areas? You lose heat. So Mercury, because of its small size, lost its heat earlier on, which means its central core has solidified. It doesn't have a molten core with heat rising up. So for that reason, it doesn't have any geological activities. It doesn't have volcanoes. It doesn't have tectonic plates. So its surfaces can't get renewed. So that is why you see it all pockmarked with craters. Close to the sun and its small size. Because of no atmosphere, we take for granted our atmosphere sort of moderates our temperatures. We don't get huge temperature swings on Earth as such. But because of that, in the daytime, it gets up to about 430 degrees Celsius, considering water boils at 100 degrees Celsius. Nighttime on Mercury, it gets to minus 173. Water freezes at 0. So there you go, huge extreme temperature swings, and it looks pockmarked, and that's why. So let's put Mercury back in its little spot. What's the next planet out? Venus, and Venus was her name, yeah, absolutely. There it is. Venus is 2/3 of the way out, so from the sun compared with Earth, so it's 2/3 of an AU. That's Venus there. Venus is a very similar size to Earth, and historically it's always been called Earth's sister planet. But that's where the similarity ends, right there in its size. So what's your impression of Venus? It looks pretty bland, doesn't it? Pretty featureless. And the reason it looks bland and featureless is it's enshrouded, the whole planet's enshrouded with thick, dense, opaque, and toxic sulfuric acid clouds. You can't see through them. They're thick, very, very opaque, and very toxic. It's known as the evening or the morning star, historically, for 2 reasons. One is it's very bright in the sky. Why is it very bright in the sky? 3 reasons. One is it's very close to the sun, so reflect a lot of light, and it's close to us, so we see most of that reflect light. But the other reason is clouds are very good at reflecting light, very reflective. So for those reasons, it appears very bright in the sky. As I showed you, its orbit is inside the orbit of Earth's orbit. So from our perspective, it always appears to hug the sun. So we see it just after sunset and just before sunrise. So hence its nickname, the evening star or the morning star. If you see a really bright light on the horizon, it's not twinkling and it's just before sunrise or just after sunset, there's every chance it'll be Venus. Okay, so this is a radar image. So NASA's Magellan orbiter went to Venus and used radar to penetrate through the clouds. And this is pretty much what they saw. It's just a vast array of volcanoes and lava fields. Very, very geologically active. No tectonic plates, but volcanism is very extreme. Because of that, it's got a very young surface, somewhere between 300 and 600 million years, its surface. So just constantly getting renewed with all that volcanic activity. So that was very cool. They could start seeing through the clouds with radar. This here is a computer simulation, generated picture of what the surface would look like. They look at the radar and the computers build it all up and say, well, if we were down there, this is what we would see. And once again, you can see in the back there, big volcano, but look, all that sort of lava fields, just flat lava fields. So that's what the surface of Venus would look like. But you're in for a treat shortly. The other thing to mention is that its atmosphere is really, really thick. Why is that so? Intense volcanic activity, just constantly spewing out carbon dioxide. But the other thing is, there's a lot of evidence to suggest that Venus once had oceans. And on Earth, you might say, well, why is our atmosphere, it's reasonably thick, but it's not overly thick. To give you how thick it is, the atmospheric pressure on Earth at sea level is considered 1 bar. That's a unit. The pressure on Venus is 93 times that. You'd be crushed instantly. Why is that so? On Earth, volcanoes spew out carbon dioxide, but we've got big oceans, and oceans are wonderful absorbers of carbon dioxide. They often call it a carbon dioxide sink. That just attracts carbon dioxide. And there's evidence to suggest that Venus did have oceans once, but being so close to the sun, the oceans just eventually evaporated and boiled away. So you've got volcanoes spewing out large amounts of carbon dioxide, excessive amounts, because you saw it's a really volcanically active planet, but you've got no oceans to absorb it. So the CO2 just builds up and up and up. And of course, that causes the greenhouse effect, which we're probably familiar with that term, how it's a runaway episode where the carbon dioxide adds more heat, that then retains heat, and it just snowballs from there. Because of that, Venus, not Mercury, Venus is the hottest place in the solar system, 460 degrees Celsius. Consider this, lead melts at 330 degrees Celsius. And here we are, 460. So if you miraculously put yourself on the surface of Venus, you're pretty much instantly going to be cooked and crushed pretty smartly. Wouldn't look good, guys. So that's the atmospheric conditions on Venus. And importantly, you know now the atmospheric conditions, but importantly, you know why it's like that. Here's my little treat that I mentioned. So the Russians have had 4 landers on Venus, Venera, and this is some photographs from Venera 13, 1982. Not surprisingly, they only survive an hour or so. So obviously it's metals and stuff, but the metals and particularly the electronics all just start melting and going crazy, shutting down, and then the whole lander would eventually just get crushed, melted. So here's some view here. That's from the front camera, and there's from the rear camera there. And look how smooth, look, it's just, this is obviously in a lava field. Look, there's plates of it's just gravel, dust, and flat lava, plates of lava rock. The other thing you'll notice the dim lighting. They're very dim, and the yellow appearance of the sky. That is because of the clouds. The clouds reflect 90% of the light. So you're only getting 10% of your sunlight through the clouds, and that gives that very dim lighting and the yellow sky sort of appearance. So there you go. You could go home and tell people you've seen what it's like on the surface of Venus. So let's put Venus back in its little posse over there. What's next? Earth, us, third rock from the sun. 1 astronomical units from the sun, 150 million kilometers. This was the image I showed the other day from the Apollo 17 mission in 1972. And as I mentioned, just very briefly, as the astronaut who took the photograph said, what did we learn? We learned how isolated, fragile, and vulnerable Earth is with that photograph. Just magnificent. So Earth is home to about 400 million cats. Those are my cats. That's Boston. He loves to come out observing with me. That's Maya, and that's Mischief Stella. Always trouble. 8 billion of us humans. 8 billion of us walking around. So you're probably familiar with a lot of this, but let's just recap, because once again, let's say why. 70% of the surface is covered with water, and of course that's critical for carbon-based complex life. How did the water get here? Probably through asteroids and comets, the evidence seems to point to, and a little bit of water sort of mixed in with the chemicals and the rocks and so on that's come up from below as well. And someone once said to me, gosh, that's a lot of water. I said, 2 things. One is, there's also a lot of comets and asteroids out there, but the second thing is, we think we've got a lot of water. Europa, one of the moons around Jupiter, is less, just a little bit smaller than our moon, which is only a quarter of the size, volume, diameter-wise, of Earth, and it's got twice as much water as Earth. Put it in perspective. The moon of Titan, a little bit bigger than our moon, has got up to 10 times the amount of water on Earth. So yeah, it's not over the top. It's just we've got a reasonable amount of water, but by no means considered excessive. Our atmosphere is mainly nitrogen that's outgassing from volcanoes, along with the CO2, and we've got oxygen. That's what separates our atmosphere from a lot of other atmospheres. We have oxygen that's come from the process of photosynthesis, from microbes and plants generating oxygen from carbon dioxide. Fossil evidence suggests life got started on Earth around 4.1 billion years ago, but it was simple life for over 3 billion years. It was only 650 billion years ago that complex life like plants and animals were able to come along. And why? Oxygen was the key to that. So let's put Earth back. We don't need to talk more about us. What's next? Mars, yeah, the red planet. It's 1.5, so it's half a distance again out. So you can see there, they're all, these 4 small inner rocky planets are all relatively close together to one another. So there's Mars. This is a lovely image from the Hubble Space Telescope. And your first impressions of the appearance, it's red, isn't it? And that's because of iron oxide. It's very rich in its soil. Rust, essentially. Its soil is very rusty. So it appears very red. You've got a polar cap, north and south. That's frozen water and frozen carbon dioxide. You've got these dark areas in the lower southern areas. That's the highlands. So those are mountains rising up above all the dust and so on. And you've got a bit of cloud in here too, a bit of ice that's condensed on dust particles within the atmosphere. So those are the first things that you happen to see. Size-wise, it's about half the size, diameter-wise, as Earth. And that is a reason why it is as it is. Earth, as you know, because it's got a molten core, it's hanging onto its heat, its core, iron core is still molten and sloshing around. And that we talked about the other day how it generates magnetic fields going around Earth, and that deflects a lot of the particles from the solar wind, eroding our atmosphere. Mars, because it is relatively small, has cooled down, and its once molten core is now solid. So it's lost its global magnetosphere. Because of that, its atmosphere has been stripped right away. The other thing is, well, one third the surface gravity. So if you're 90 kilograms here, go there and you're only 30. Great way of losing weight. You can still eat your ice cream. So its very atmosphere got eroded away, so it's got a very, very thin atmosphere. The atmospheric pressure on Mars is less than 1% that on Earth. Very, very thin atmosphere. Because of the very thin atmosphere, it's also very cold. Average temperature on Mars is minus 60 degrees Celsius. Almost as cold as a student flat in the wintertime. It's mainly carbon dioxide. It doesn't have oxygen because there's been no plant life there and microbes that we can identify that's produced oxygen along the way. You might say, how about nitrogen there? Nitrogen, Earth's got lots of nitrogen. As the atmosphere got stripped away and the harsh ultraviolet light from the sun, it split the nitrogen up and nitrogen just drifted away a lot. So it's just left with the carbon dioxide. So 95% carbon dioxide. Okay, so there have been a lot of landers, but there's been 5 rovers that have landed on Mars, and a lot of what we know about Mars has come from these rovers. The most recent one, or there's 2 still active, Curiosity and Perseverance, and this is an animated video of Perseverance landing on Mars in 2021. You'll see it's fully operated, and they use a process called a sky crane. You'll see what's called a sky crane. Let's have a look. And this is all fully automated. NASA's got no control over this. It all happens on its own. Isn't that beautiful Marsscape? It's a massive big crater called Jezero Crater, which was once a big lake, and you can see where the water once flowed an inlet there into this massive big lake, which was once a crater. Yeah, there you go. Amazing technology, isn't it? That's how so it's all pre-programmed to do that. NASA has no control. They just hold their breath and wait till they get the signal from its lander. It's called a sky crane. So here they are here. This is in Jezero Crater, which was once a massive big lake. There's a lot of evidence for that. This image was taken by Perseverance. And impressions, you can see once again, the really red soil. So this is an actual image, and look at the red soil. That's from the iron oxide, the dust. The other thing you notice here, look at how smooth all the rocks are, all the rocks and pebbles, totally weathered completely down. It's just as smooth, if not more, than any set of rocks that you would find on Earth. So that's real picture of what it looks like on Mars. I just love looking at these pictures. Just take it in, be drawn into the picture. You think, if you're there, that's what you would see. It's not just a pretty picture, it's what you would see. This one here, the other rover that's still functioning is Curiosity. That's in a large crater called Gale Crater, which also was once a large lake. They're searching, the initial one searched for the signs of water, which was it's very clear that Mars had abundance amount of water. In fact, 3.5 billion years ago, when life was really getting underway at Earth, the evidence is that the conditions on Mars were more conducive for life on Mars at that time. There was a lot of lakes, flowing water, and so on. So they're now looking for signs of past life. Where do you go? Water. So that's why they're going to these big craters that were once covered. But I like this. Once again, you can see the red soil, smooth rocks. But I love that. That's, they call it Dingo Gap. And that's where the rover has been. So you can see man's, tracks, his disturbance of the soil on another planet. I just love it for that. I can look at that picture for so long and just take in all the details. Beautiful. The sky, notice the sky is sort of a tan colour. That's because it depends on what time of the day and how much dust has been flowing around. And that's because the atmosphere is very thin, but also there's a lot of that rust particles suspended in the atmosphere as well. So they don't have a bright blue sky like we do. That's sunset, taken by Curiosity, sunset on Mars. And you'll notice the very small sun, a dim, small sun, because it's 1.5 times as much away from the sun as we are on Earth, and sunsets a blue-grey sort of colour. The largest volcano in the solar system is on Mars. It's 3 times the height of Mount Everest, so about 25 kilometres high. Wow, imagine climbing that. 3 reasons. One is because there's evidence a lot of volcanic activity once occurred on Mars. When it was hot, of course, its interior's cooled down. Not much in the way of geological activity these days, just a few little Mars quakes, but certainly no active volcanoes, but there has been in the past. Low gravity, as I mentioned, the gravity is only 1/3 that is on Earth, which means, you get so high on Earth, and then gravity pulls rocks and pebbles and, starts pulling things down. You've only got 1/3 the gravity, so you can go up 3 times as high before gravity starts pulling stuff down and rocks start tumbling down and so on. The other thing is it doesn't have tectonic plates. It's only got one rigid plate. It's a one-plate planet, Mars. One rigid plate, which means it's more solid and sturdy. It can hold a large mountain up. Like if you get tectonic plates, you get a mountain big enough, the weight of it will start pushing that plate back down again. So it's a very one-plate planet, one big solid rigid plate. So it's able to support something like a large volcano. So there you go. There's a little bit of trivia. Where is the largest volcano on Earth? And what are you going to say? Mars, yeah. Okay, so that's Mars. Let's move on. What's the next planet? Jupiter. Yeah, there it is there. See the big jump now? 5 astronomical units out. So there's Jupiter. This is a lovely picture from the Hubble Space Telescope. Who here has seen Jupiter through a reasonable sized telescope and seen all its bands and stripes? Yeah, a few. Those of you who haven't, do yourself a favour, somehow get your hands or visit someone or visit somewhere where they have a nice telescope. That's what Jupiter looks like with your own eyes through a decent, when I say not a professional telescope, but a decent sized home telescope, that's what you see. Even 8 inches, you see that. It's the largest by far in the solar system. Diameter-wise, 11 times the diameter that of Earth's. Volume-wise, Earth would fit into Jupiter 1,300 times. So it's huge. There it is there. That's just a scale drawing. So there's Jupiter here, and there's little old Earth below. It's a big, they call it a gas giant because it's predominantly hydrogen and helium, 2 most common elements in the universe. So it's a big ball of gas. It's just there's no hard surface. It just gets denser and denser and denser as you go into it, and eventually you just get crushed by high density gas. As I mentioned, those prominent bands, and why has it got these multicolored stripes or bands, if you will? They represent zones of atmosphere with different wind speeds, different composition, and different temperatures in the atmosphere, and that's why you get that. Very famous for its great red spot. You can see that with a decent-sized telescope, anything like sort of 10, 11 inches telescope, you can see the red spot. It's like a salmon colour with your eyes, but it's really cool when you see these stuff with your own eyes. So the great red spot that Jupiter is so famous for, that's a huge storm that's been going on in its atmosphere for 400 years. It's larger than the size of Earth, that red spot, that big storm that's going on in its atmosphere. I just love these images, beautiful. What's the next planet? Saturn, yeah. Everyone loves Saturn. There it is. You've doubled. You've now gone out to 10 astronomical units. There it is there. This image was taken by NASA's Cassini orbiter back in 2008. It's a large gas giant as well, predominantly hydrogen and helium. It appears very featureless, but a sort of a tan type of colour, and that's because of a lot of hydrocarbons in its atmosphere. It's 10 times the size of Earth, diameter-wise. Very low density. If you had a bathtub big enough, Saturn would float in it. Yeah. Warning, dad joke. And if you take the plug out, it leaves a ring. Sorry, guys, I couldn't help myself. I decided last night I wouldn't mention that joke, but I got up here and couldn't help myself. It's got a prominent ring system. That's what it's most famous for, its prominent ring system. So let's have a look at that. And what that is, it's just multiple millions and millions of fragments of rock and ice and just gravel, what we call dust. So I've changed the name from dust to it's a fine gravel sort of type of stuff. And that's it there. They suspect it came about through a moon that ventured too close to its planet Saturn, and just the huge tidal forces, because Saturn is large, it just ripped the moon apart and created that ring. They estimate the ring's about 400 million years old, and there's evidence to suggest that it's recycling. There's new material coming into it, there's material going out, and it may not last forever. So we're just in a lucky window of time to enjoy it. And once again, who's seen the rings of Saturn with their own eyes through a telescope? Yeah, isn't it exciting? It's really, really cool. If you do get the chance, look at Saturn through a telescope. It's so clear and concise. It looks like a caricature, those rings. They're just beautiful. Or maybe I just get excited readily. I don't know. So let's put Saturn back. The next planet, Uranus. And remember our talk, we said that, I think it was, top of my head, it was 1781. William Herschel discovered it with his 48-inch telescope. And the span of the solar system doubled overnight. The span up to then was what was it? 3 billion kilometres, and it went out to 6, or 20 AU. So there's Uranus. Uranus looks pretty bland, doesn't it? This is an image taken by Voyager 2 as it went past it in 1986. It's 4 times the size of the Earth. Big, but nowhere near as big as those gas giants. So it is predominantly gas. It's got the atmosphere in particular is hydrogen, helium, and methane. It's the methane that gives it a blue appearance. Methane tends to absorb your red type colours and reflect your blue. It's got a lot of ice. For that reason, it's called an ice giant. It's got a lot of water, methane, and ammonia ice that predominantly make it up with the gases around it. This is with a Keck telescope, and a 10-metre telescope in Hawaii, and was able to take a picture in infrared wavelengths, and you're able to see this little ring system around it. But the key thing you notice there is Uranus is tipped up on its side. See that? It's tipped up on, so it's rotating not like that, but it's going around like that. Probably large collision. The solar system in its early stages was a pretty violent place. Then Neptune. Neptune is the same. It's about the same size as Uranus. It's a deeper blue. It's an ice giant with a thin atmosphere of the gases around it. And it's a darker blue. It's got a little bit more methane in it, but also it's got a lot of strong winds and storms going on that stirs the methane up, and it gives it that darker blue appearance. There it is there. And that image was taken in Voyager 2 in 1989. There it is there. Just love that colour. It's just so vivid, isn't it? So that's our outermost planet. So, the planets in a nutshell, yeah, as you can see there, two main planetary groups. And I can hear what you're thinking to yourselves. There's quite a few of you without your tin hats on, so I'm connecting. I can hear what you're saying. Why is that so? Why? Let's have a look. The four inner planets, Venus, Mercury, Earth, Mars, all significantly closest, but the small, dense and solid objects dominated by rocks. Rocks are predominantly silicon oxygen. Four outer giants that we've looked at, Jupiter, Saturn, Uranus, Neptune, much further out from the sun, large, low density, ill-defined surfaces dominated by hydrogen and helium gases, along with some water, methane and ammonia ices. Why is that so? Let's make some sense out of it all. There's I just did that crude diagram there, just with the character, just to show you you see the dichotomy? They call that a dichotomy. Two distinct, separate groups. Why? Two reasons. One is the universal abundance of elements, which we'll look at. There's not equal amount of all elements in the universe. And we're going to talk about the protoplanetary disk. We touched upon it the other day. That forms as the sun formed itself, rotating faster and faster. Centrifugal forces set out a disk around it, and that disk gets very hot. So let's look at first of all, the universal abundance of elements. 98% of all the elements throughout the universe is hydrogen and helium. Can't emphasize that enough. That's really important. So, of course, hydrogen and helium provides the material for the gases, for the gas giants. Yeah, extreme amounts of hydrogen and helium to make gas. Oxygen, carbon and nitrogen are the next most abundant elements. They make up between them only about 2% of the elements in the universe, the entire universe. So of course they go to make up, so hydrogen, when it combines with oxygen, makes H2O, water. Hydrogen, when it reacts with carbon, makes CH4, which is your methane. Hydrogen, when it combines with nitrogen, makes your methane. So there's a picture there that's going on. By the way, why with hydrogen? Hydrogen is very, very reactive, and helium is an inert gas, doesn't react with anything. It's only good for MRI scanners and party balloons. So the hydrogen is really, really reactive, so it's on its own, but when it combines with these ones, it gives the ices. And then there's just trace amounts of your silicons and your magnesium and manganese and so on that go to make up your rocks and your metals. So that's an important concept. Just hold that thought for a moment. Here is your big disk. So you've got your the big protostar, say in the middle there. Say it's a young sun that's just forming. This huge big disk, circumstellar disk forms around it, and it gets really, really hot. Eventually, all this material gets vaporized. It's so hot. And it's hotter in the middle and cooler. That makes sense, doesn't it? It's hotter close to the hot star that's forming. And what we call is a temperature gradient forms. So here is your proto-sun. It gets cooler as you go out. The temperatures in here, before the gases start to condense into solids, you're talking about, it's about 2,000 degrees Celsius here. You get out to 0 degrees, that's where ices start forming. Water freezes at 0 degrees, and it gets out into the cold areas about minus 250. Let's just lift that up a little bit. I'm very much people in the front row. I've made a point of lifting the whole thing up so you can see what I've written there. A concept is different materials condense out at different temperatures. That's an important little concept. Metals and rock will condense to solids throughout the whole disk. They can remain solid in high temperatures. You put a high temperature to a bit of metal, it doesn't necessarily melt. And ice will melt where metal won't melt. And so your metals and your rocks, they start forming into solids reasonably close to 2,000 degrees, and throughout remember, there's just only a relatively small amount of them, but they are solids right throughout the whole disk. Ices can only condense from about 0 degrees outwards. So in this region here, it's too hot for ices to condense into solids. And remember, there's moderate amounts of ice, certainly nowhere near the gases, but much more material to make your ices, your water, your methane, and your ammonia ices than your metals. I'm just going to bring that back. So what happens then, as the planets start forming, the inner planets, all they've got to have to deal with and make into planets, just a small amount of rock and metal to form 4 small inner planets. Further out, about halfway out, it gets to 0 degrees, and anything out from there, ices. So suddenly you've got a small rocky core. Those other planets are just small rocks. But you can gather some ice, and there's much more ice than rocky material. So suddenly you've got a small rocky core, a moderate amount of ice around there, and from there you've got a critical amount to attract all your hydrogen helium gas that will then bind to those ice planets that are forming. And as you know, there's extreme amounts of hydrogen helium. And it's that whole process is why you get this. So in the inner solar system, there's only rock and metals, the only things that can solidify. There's only a small amount with them, so you get these 4 smaller guys. You start getting ices, so you get your ice giants and so on, but also that's enough to attract the gas, which is oodles and oodles of hydrogen and helium, 98% of the universe. So there you go. That's why you get 4 inner small rocky planets, and you get large ice and gas giants in the outer solar system, where it was cooler when that disk was first forming. So the next question is, why is Pluto no longer a planet? That's a frequently asked question. Some people argue it never was. So let's have a look at Pluto. There it is there. In 2006, it was demoted to a dwarf planet. What happened, dear Pluto? Well, it all came about is that in 1930, Pluto was discovered, and so there were 9 planets. And life was good. We all had our little mnemonics and what have you at school. You knew your 9 planets. And then in the 1990s, these huge, big 10-meter across telescopes, much more powerful, were able to look into the outer parts of the solar system. And they discovered planet after planet after planet. They realized where Pluto was. There were thousands, if not millions, of objects of comparable size. And they thought it was pretty unfair for little Johnny to be going home and practicing as naming 20,000 planets to his mums. So probably the mums got together and said, look, we can't have our kids coming home trying to learn the names of 20,000 different planets. So they realised, look, hey, we've got to reclassify what planets are here. There's more to the solar system than we really thought. So they made these 3 criteria for planets. They said, 1, it's got to orbit the sun. You might think, well, that's common sense. That separates it from, say, a moon that goes around a planet. It's got to be round. To be round, you've got to have enough mass or matter for gravity to mold you into a round shape. Very rule of thumb, rough guideline, you've got to be at least about 500 kilometres across. Anything smaller than that, look at some of those asteroids and stuff, they look like potatoes. They're just small, oblong sort of things. They're not big enough. They don't have enough mass to mold, for gravity to mold them into being round. So they made that a criteria to be a planet. The other one, and this is where Pluto fell down. So Pluto orbited the sun. It was large enough to be round, but it didn't dominate its orbit. It didn't what we call clear the neighbourhood. The third criteria says that there must be no other objects of comparable size in the same orbit. You can't share the orbit with another object comparable size. And that's where Pluto fell down, because of all those thousands, if not millions, of smaller objects in the area. Some are very similar size to Pluto, they even found as well. Now, it's not all bad news. The Plutonians might have been upset. Oh, we're no longer a planet. maybe they didn't care. But Pluto then got called what we call a dwarf planet. So they met a new criteria. And the good news for some bodies out there, like there's an asteroid Ceres in the asteroid belt, and that orbits the sun, but it's big enough to be round. So instead of just being called an asteroid, Ceres was called a dwarf planet. So it got promoted. So it wasn't all bad news. Plutonians were upset, but the Sirians were okay about it. So there you go. So that is the logic why Pluto. So it's not all bad. It's just been called a dwarf planet, and it just makes sense and easier to classify things. And that, my friends, is a journey through the solar system, the sun and planet through modern eyes. Thank you very much. Two comments. One is, I know I've fire-hosed you with a lot of information today. There is there's a 2-page handout that spells it all out, or email me for a copy of all the handouts PDF. And the second thing is, this was my last talk. I get off at Auckland. So thank you for your support. Thank you very much. Farewell and enjoy the rest of your trip on the beautiful, elegant Volendam. Thank you.